Good afternoon, everyone. I'm Bowen. Today, I'd like to presenting on motion state identification with multimodal sensor data from iPhones. My objective is to classify human motion status. The dataset I use comes from a university experiment called Motion Sensors Dataset. They use iPhone 6s to collect data. We also know that there are so many sensors on iPhone, such as accelerometer, gyroscope, and attitude sensors. The label or the output of my algorithm is 6 activities, such as the going downstairs, upstairs, sitting, standing, working, and jogging. Okay. The input of my algorithm is user acceleration, gravity, rotation rate, and attitude angles. User acceleration is linear acceleration during movement. Gravity is human gravity. The rotation rate is rotation of body during dynamic activities, and the attitude angle is the orientation of an object in 3 dimensions. The input is 12 features. This is because each of them have x, y, z 3 dimensions. Okay, let's move on. The sensor simply rate is 50 Hz, and the dataset is time series data. I choose 10 seconds as an time windows. So the input data set for each batch is 500 times 12 feature. The time series data is the input of the feed-forward neural network and the recurrency neural network. I also want to try some new things. I changed the time series data to vision feature to train the image classification part. Let's move on. For the time series length is 500 and the feature is 12. So we also want to know each time step, the distance between each time step to all of these time steps. So the output of the recurrency plot is 500 times 500. That also means it's the pixel of the recurrency plot is 500 times 500. The recurrency plot is the input of the image classification part. Let's move on. Here is the example for the recurrency plot. It's the working, standing, and the downstairs sitting. It's easy for us to distinguish this picture, and I think it's also easier for the algorithm to distinguish them. Okay. In this part, I'd like to introduce the image classification models. On my dataset, I tried 3 different models: ResNet, Bayesian transformer, and swing transformer. First, let's talk about ResNet. ResNet is a network introduced by Kai-Ming He and his team in 2015. This convolutional neural network solved the vanishing gradient problem by using residual connections. This allowed information pass through the layers more easily. ResNet achieved higher accuracy and faster convergence in image classification tasks. Next, we talk about the vision transformer. Vision transformer introduced by the Google research in 2020. And the transformer architecture originally built for language processing. The vision transformer applied this to image. Let's move on. The next part is the swing transformer. Swing transformer created by the Microsoft research in 2021. It built like a convolutional neural network. This is because it used the patch merging to reduce the feature maps and increase the number of the channel. It's similar like the pooling. in the convolutional neural network. Okay, all of these algorithms we used from the Python package called KIMN. And the platform we use is created by the Facebook research. Okay, let's move on. Okay, for this picture, it's the top one accuracy for the test dataset. We can see that the test accuracy for feed-forward neural network is it's the highest, and compared to the three different image classification model, the Bayesian transformer is has the worst result. Let's move on. Okay, this slide shows the training loss values. We can observe that the training loss of feed-forward neural network is the smallest compared to another algorithm. Let's move on. Okay. However, when we look at the third slide, we notice that the test loss is not significantly better than the other algorithm. This is because we use cross-entropy loss. Now, let's look at the table on the left. We can see that the proper probability of working is 50%. Compared to other classes, this is highest probability, which also means that the accuracy is the highest. However, since the 0.5 is not close to 1, its loss value, the loss value of the left algorithm is quite large. In contrast, in the table on the right, the accuracy is 95%, which means the loss value at this point is very small. So that's the reason why the test loss is very high. It's higher, but the top one accuracy is very high too. Okay. Let's move on. We can find that the convolutional neural network and swing transformer is more better than the Bayesian transformer. This is because the Bayesian transformer, let's see the picture 6. We can see in the first slide, the patch windows is 16 times 16, and in the next layer is 8 times 8. That means the swing transformer and convolutional neural network can extract the feature from the different dimensions. So it can learn more information than Bayesian transformer. So it's better than Bayesian transformer. Let's move on. Finally, we talk about the limitation of the experiment. The first limitation is the number of images. For my dataset, for my training dataset, it only have 4,000 images and 1,000 images for test dataset. I think they are not enough for the image classification model to learn. And then we also know that, this is a mistake. For each time series windows is 10 seconds. So if we choose 20 seconds as the so if we choose 20 seconds, the number of the picture will only 2,000. Here is the mistake. I will change. I will change it before. It is difficult for the algorithm to learn. And the next limitation is data imbalance. Some classes like sitting, working, they have 1,000 pictures, and others have 400 pictures. It's difficult for the algorithm to learn all the feature of all the labels. The last limitation is because of the data. You know, my data comes from the experiments, so the performance of the algorithm may not good in the real world. Well, here is the reference list, and thank you for everyone.